In this section, we'll discuss about reactions involving aldehydes and ketones. Silver nitrate is a mild oxidizing agent. So if you have an aldehyde, so RCHO, R could be any alkyl group, it could be CH3CHO. So if R is CH3CHO, this is what you're going to get. So if I have CH3 and then C double bond OH, this is going to give you CH3 then COOH. So basically aldehyde is going to be oxidized to carboxylic acid. In this slide we're going to discuss addition of H2O to carbonyl group. Carbonyl group is this, C double bond O. Now let me remind you, in carbonyl group carbon is positive, and I hope you remember that why carbon is positive, because oxygen is more electronegative than carbon and pulls electron away from carbon. So here water has these pairs of electrons and that pairs of electron would be attracted to positively charged carbon, and temporarily that carbon would have too many bonds, so it has to give up its pi bond and is going to dump its electron pair onto oxygen. So this is what you're going to get before you get the final product. So let me show you with a different color arrow, and then I'm going to show you CH3 C CH3. Remember, water got bonded now, OH2 plus. So there'll be a plus here. Oxygen used up one of its electron pair. The other electron pair is already sitting on oxygen. If you want to count, it's a 2 solely on oxygen, then it gets 3 shared electrons from 3 bonds. So 2, 3, 4, 5. And neutral oxygen is supposed to have 6 valence electrons. So it has 1 fewer electron, for which oxygen is plus or plus 1. Now, this oxygen has now extra electron, so that's minus 1 or minus. Then this hydrogen gets out of here at H plus, so it gets out, and it's basically this one picks up the hydrogen. And finally you have 2 OH group and you end up with this compound. So if you remember the mechanism that how reaction can happen, you can predict a product formation. You don't have to memorize each and every reaction. Now here we are showing you addition of alcohol to carbonyl carbon. So this is again the same story. CH3OH, if I write down a little differently so that you can see similarity between addition of water and addition of alcohol, methyl alcohol. You have a methyl group here, so CH3, and then you have oxygen, just like water. 4 electrons solely on oxygen, and that's attracted to this positively charged carbon of carbonyl carbon, so it gets over there. And just like before, this double bond has to be broken, dumping electron onto the oxygen. So oxygen becomes O minus, and that's basically what you have now. So just like before, this oxygen picks up H plus, O minus picks up H plus, becoming OH, and then this CH3OH plus, it becomes plus and loses this H plus and becomes OCH3. This kind of bonding is called hemiacetal. Now let me explain to you what is hemiacetal bonding. You have a carbon on one side, you have ether linkage. This is ether. Let me show you, COCH3. This is ether functional group, and also there is one OH functional group. So ether and alcohol, both functional groups are present here. and that's called hemiacetal. If I allow another molecule of methyl alcohol CH3OH to react with hemiacetal, then because of the presence of H+, this OH, let me show you the OH with a different color. This OH becomes H2O. Let me show you that separately. I think it got a little messy. So I'm going to redraw that so that you can follow it. So hexagonal ring, that's the hexagonal ring. And that carbon has OCH3, OCH3, and OH. Now because of this H+, it sees this electron pair is going to bind that H+. So that would give you H2O. So eventually H2O gets separated. So when H2O gets out of here, then you'd have a positive charge here. That's going to attract CH3OH. And that's exactly how OCH3 gets bonded from the second molecule of CH3OH. So this addition is pretty much like addition of H2O. But this time there are two ether groups. You can see this is the carbon with COC on one side and COC on the other side. So basically you would have, this is C of the ring structure, and you have OC on one side and OC on the other side. So there are two ether groups, and that's called acetal. Acetals are quite stable and they're not like hemiacetal. So it often, scientists use it as a protecting group to protect some aldehydes and ketones, especially aldehydes when they undergo oxidation reaction quite readily. Now this is a very good example of how scientists can design an experiment. So if your intention is to go from this compound to the compound on the right, now if you think that you're going to use lithium aluminum hydride reacts with this ketone group as well as ester group, COOCH3, and you would end up with this product, which is not a desired one, because the desired product has C double bond O. So in other words, we want to keep carbonyl group in the fourth location intact. In order to keep it intact, you ought to first attach another group and protect this carbonyl group. Now we're showing you how this can be possible. So we're using methyl alcohol as a protecting group. So two moles of methyl alcohol is going to bind with this carbonyl group and gives you acetal. So this is the acetal. Then you should allow lithium aluminum hydride. Remember lithium aluminum hydride, that's going to offer H- in the reaction. So basically H- is released from lithium aluminum hydride, and that's going to react with this carbon. Then carbon is going to give O-, and finally it's going to push out OCH3 group as CH3OH. That's what you see here, and then eventually get OH. So let me show you this step so that you don't need to really memorize. I'm trying to cut down your memorization time. I'm just going to show you this segment of this reaction. So let me show you that. C, then hydrogen gets bonded here, and then you have O-, and OCH3. Now OCH3 can pick up hydrogen from H3O+. So basically it becomes CH3OH, and that would be a good living group. This is the methyl alcohol. Neutral molecules are always a good living group. So that gets out, that's pushed out. So you can get CHO aldehyde and then aldehyde reacts with another mole of lithium aluminum hydride or another H minus coming from lithium aluminum hydride and gives you this product. And H3O plus adds H plus to a negatively charged oxygen. So if you write yourself, and then you should be able to predict the final product of the reaction. There are a few other reactions. I mean, I don't expect that you're going to memorize these, but the idea is to learn the mechanism. Mechanism is very similar. Electron pair is always attracted towards a positively charged carbon. So here you can see that nitrogen with electron pair is attracted to this carbon, carbonyl carbon. Carbonyl carbon is carbon that contains the double bonded O. So that's why arrowhead goes from nitrogen electron pair to carbon, and that gives you, let me show you, at least the first step you should be able to predict, and that would lead you to the right answer. So let me show you that. This is 6-membered ring. Now gets O minus on this end, and you'd have NH2 here because nitrogen uses this pair of electron. So NH2, then OH, and that becomes plus, because in sharing nitrogen lost one of his electrons, valence electron, so it became N plus. Okay, now I'm not going to show you any additional steps because it's finally this goes out with as H2O. First it picks up hydrogen as H plus, but forms OH, and then it picks another hydrogen giving H2O. Then finally that H2O leaves, and then there'll be bond formation between these two. Let me write in dotted line. Again, this is a similar reaction. I'm talking about a mechanism-wise similar reaction. So here you know nitrogen with pair of electron again will be attracted towards carbon, and then finally you get a product like this. This is an extremely important reaction. Always whenever you see an Grignard reaction, there's so much extensively applied. So I'd like you to know these reactions and understand the mechanism. And these mechanisms are much better known than many other mechanisms. In some mechanisms we can predict first couple of steps, but still that helps. But in this case, we fully understand the mechanism of the reaction. So first, there is a Grignard reagent like this. So this is cyclohexyl magnesium bromide. So obviously cyclohexyl, this carbon is negative. Normally carbons are positive, but in Grignard reagents, carbons are negative. And those carbons are very reactive. So those carbon with pair of electron, it goes from here to positively charged carbon in here. So it goes in here, so that's carbon. And then this bond is broken. Otherwise carbon would have too many bonds. So basically what you're getting is the following. I'll show you one intermediate step, because for exam this kind of reactions are very important. So I strongly suggest that you know this. So this carbon goes to that carbonyl carbon with two hydrogens, so that has two hydrogens, and since double bond is broken and it dumps this electron onto oxygen, so oxygen would have extra electron and get -1. So this is what you're going to get at this level, and then it picks up H plus in the reaction and it gives you CH2OH. So it's called cyclohexyl methanol. So if you know a mechanism, it would guide you to right answer. So basically you get an alcohol. When aldehyde or ketone reacts with a Grignard reagent, you end up with an alcohol, OH at the end. Now here we're showing you a few other mechanisms of reaction. You can see that here is the symbolic one, and it's not showing any particular nucleophile, just it's written down as Nu. Nu means something that is attracted to carbon, positively charged carbon. So basically I've shown you this nucleophile when it reacts with this carbon, the double bond breaks down, and then you finally get this negative charged oxygen, and then H3O plus provides H plus, and you finally get this. So we already discussed that. Even in last slide we mentioned this. Sometimes you may have unsaturation, like in this particular case, in second case, alpha beta unsaturation. So you may have an aldehyde or ketone, which we call alpha beta unsaturated aldehyde or ketone. In those kind of cases also, you can see that how electron charges can redistribute from one center to the other. If you focus on this oxygen, you have a negative charge there, and because of resonance, it gives you charge on this carbon. How does it happen? Let me show you one step. This electron pair comes in between this, and then the carbon gets too many bonds, so it has to dump its electron onto adjacent carbon. So that's why this adjacent carbon gets electron pair and negative charge. And eventually H3O plus supplies H plus, and you get hydrogen attached to this negatively charged carbon. Again, this is another example is shown. This is CH3NH2. I think it's hard to read this. CH3NH2. Again, here you have a nitrogen with pair of electron. If you look at the location where nitrogen gets bonded, keep this in mind. This is an additional product in addition to reaction at carbonyl carbon. This is carbonyl carbon. So that carbon is positive. However, this carbon, I'm showing you with the red asterisk, also has some positive character because of conjugated system. That means conjugated means double bond, single bond, double bond. That's called conjugated. Now, how does it work? This double bond with electron pair goes to this carbon, and then this carbon is going to dump its electron pair onto oxygen. So that means this carbon gets plus. Since it's plus, nitrogen is attracted to this plus, and it's going to give you this compound eventually after loss of hydrogen. So in other words, not only this carbonyl carbon is positive, this carbon also is positive because of resonance. Here we are showing you Grignard reagent, and again you need alkyl halide and magnesium. That would give you Grignard reagent. And here we're just wanted you to know that this reaction cannot happen if this group where you have the hydrogen Fg is OH, NH, or any acidic group. Then reaction is going to happen within that molecule. In that case, Grignard reagent is not going to work. Now this is a biological addition reaction. We can say within the molecule there is a reaction happening between OH and aldehyde group, and that's forming cyclic hemiacetal form of sugar. In this slide we are showing you a reaction between a carboxylic acid and ammonia, where ammonia, nitrogen has a pair of electron, and that it donates its electron pair to carbonyl carbon, And eventually that gives you this product with carbon double bond NH group. And after reduction of that, you end up with alanine. This is CH3CH NH2COOH.